Okay, so differentiable inductive logic programming. So this is, I think, a very interesting topic. Inductive logic programming deals with learning a logic program, so learning a set of rules from data. And there was work before inductive logic programming where rules were learned from data, and these were things like FOIL, a priori, that had much more of a data mining feel. And really, it started with this guy, Stephen Muggleton, out of the UK, and his approach was, hey, none of this other stuff that's learning rules is really learning a logic program. So there's no guarantees of entailment or consistency or anything like that that we care about. There's no notion of inference steps. So there's no idea, when you do something with the a priori algorithm, there's no intuition that the rules you learn would be the same as if you support multiple steps of inference. And so he approached it in a more principled way and kicked off a new subfield of AI called inductive logic programming. Differentiable inductive logic programming is using a gradient-based approach to learn the logic program in a way that also handles noisy data. Traditionally, inductive logic programming has involved really dealing with the classical logic case. And here, one of the main contributions was to extend it to the fuzzy logic case. So here's a brief overview of what we're going to talk about. I'll give a little bit of background on dILP, particularly as it relates to the paper we're discussing. Then I'll talk about dILP by solving the satisfaction problem, which is also the overall approach they take. And then I'll get into some details on the neural architecture. I'll talk about the shortcomings of this approach, which are primarily around complexity in terms of the number of weights you need in this neural architecture. And then I'll finish up with the experiments. All right, so a little bit of background on dILP. And so what we have here is we're assuming a first order logic, and we have predicates. If we have a set of constants, and we have a set of variable symbols. An atom formed with predicates and constants is ground, with variable symbols is non-ground. We have rules that are of the form if P of X, then Q of X, and that's an example of a non-ground rule. We have facts. And we also, so everything here has been really right in line with the logic intro I gave a couple months back, except there is a limit on the number of inference steps. And this is a little bit of a departure. Whereas with classical logic and generalized annotated programs and all that stuff, when they have the fixed point operator, they're just going to keep applying that fixed point operator until you reach convergence. Here it's a little different. We're saying, hey, we have this parameter t, not to be confused with the fixed point operator t. It's a different context here. We're only going to take t number of inference steps. Okay? Now, practically, there's an obvious reason for this. And that is, if you want to learn logical rules correctly and consider multiple inference steps, you essentially have to replicate your neural architecture once for each inference step. And if you remember, in the classical case, the number of applications of the fixed point operator would be, you would guarantee convergence in the number of ground atoms, because each application of the fixed point operator, if it doesn't change any ground atoms, it's done. So it always has to change at least one. And changing one, is the very minimum. So you could have n, where n is the number of ground atoms applications. Now, if you're dealing with the fuzzy case, it's actually going to be much more. because now you have real values in the interval 0, 1 associated with each ground atom. So now each ground atom, that real value can change by whatever the smallest amount it can change by. And so usually that's going to be based on the number of bits you're using to represent that number. So that's going to be a lot if you let it go to convergence. So for purposes of this, and as you'll see when we talk about complexity, is there already is like a really extensive neural structure. And they just say, well, we're only going to allow for so many different steps. Now, one thing that I think would be interesting for future work that I haven't seen anyone talk about yet is if you contrive a problem where you know it's going to take multiple inference steps and you learn it with only a small number, will it still be accurate when it's applied to an instance that requires more? And this is, you could probably come up with this on your own. There could be cases where the training samples may only require a small number, maybe a couple of the training samples might require more than T, but they only go to T, but maybe that's good enough. We don't know. I think there wouldn't be a theoretical argument for that, but there probably could be some strong empirical evidence. It seems like you probably don't need to build out the neural structure for the theoretical would be my intuition. So I don't know. All right, so in their architecture, they say predicates can have up to 2 arguments. So they limit that. This is the same limitation that is applied to deep ontological nets from a couple lessons ago, Professor Samari. Now we have a new modification to the definition of predicates. We have this idea of an extensional predicate. This means an extensional predicate can never be inferred from a rule. Okay, so we could think of that be something like, we're on planet Earth, or we're in Arizona maybe, and we're only reasoning about us while we're in Arizona. Something that instantiates the problem as part of your facts, but never changes. Intentional predicate that may appear in the rule head. Okay? Some of the intentional predicates can be what we call invented predicates. One of the big things with inductive logic programming is because, unlike the traditional data mining rule learning, we're supporting multiple steps of inference. If we allow for predicates to be invented, that can help us solve the problem along the way, because we can infer these maybe latent things that we don't quite know what they are, but it puts a symbol there for us. And it'll use that in the next step of inference to draw a conclusion. And this provides a lot of flexibility in combining rules in different ways. Finally, we have target predicates, and that's what we're looking to predict. So because this is a gradient-based approach, using training samples, we have a loss function. And so we have to decide what that loss function is with respect to, and so the target predicate is what we pick for that. Notice, the target predicate is clearly going to be intentional, but not all intentional predicates will be target predicates. I can have other intentional predicates that maybe I don't care if there's a little bit of inaccuracy in when those things are concluded, provided that the target is properly concluded. And you could imagine cases like this where maybe there's some intermediate intentional predicates that in some samples I observe, maybe others I don't. And I want to consider it when that information is there, but I don't necessarily need to include it in the loss. Okay, so an inductive logic programming problem. So we have a tuple, consists of 3 things. B is a set of facts. P is a set of positive ground atoms. N is a set of negative ground atoms. And so notice that those ground atoms in P and N, they're all formed with the target predicate. Now, we are doing the first order logic case. So while we, in this paper, I think they only predict one target predicate in everything they do, there are still multiple ground atoms associated with that target predicate, okay? So maybe we want to predict, people wearing hats. And it could be any number of us who wear hats, and it's going to make an individual prediction for each. So this essentially specifies a rule, and the solution is a set of rules such that the rule union with the knowledge base, the basic facts, entail everything in positive and do not entail everything in the negative sense. And so this is the definition of a solution. Now, what this leads to traditionally in inductive logic programming is a little bit of brittleness. Because, of course, the real world has noisy data, and if you find something that for one tuple fits this precisely, there may be another tuple that just has that one extra ground end, that one guy that's wearing a hat that for no reason in the data set we could, create a rule about. But he just happened to do that to screw everything up. And so, that's where you run into trouble. Now, also note that for a tuple, from a machine learning standpoint, we can think of that as an individual sample. Later in the talk, we'll see how the authors do something that's really interesting in training their model. When they do their batches in stochastic gradient descent, they take sample constants out of the samples. So that extra step I thought was really interesting. And the reason they did this is they claim that it increases the generality of the model. And if you think about it, you can understand that intuition. Let's talk about framing ILP as a satisfiability problem. So of course, we all know satisfiability is finding an assignment of Boolean variables that satisfies a given formula. And so this is kind of the approach they take. So first we have this idea of a template. A template is specifying a way to generate clauses, candidate rules. Okay, so we have, so for a given template, there's a whole bunch of potential rules based on that template that we want to consider. And so what we do is with each clause generated from one or more templates, we tack onto that clause one more ground atom, and that's a flag, okay? So we don't consider any constants or variables with this ground atom. We just treat it propositionally or as a predicate with, no arguments. So what we do is we're looking to find assignments to these Booleans such that the resulting clauses that have a positive Boolean associated with it union with the facts entail the positive examples. So essentially what we're saying is, we're saying that, hey, our solution to this ILP problem, it's this whole huge program consisting of all these clauses generated by the templates. And with each template, there's just an additional atom. And so the ones that have the positive, those are going to actually work. Everything else is essentially switched off. But the way you need to think about this to understand the learning is all that stuff from the templates is in the logic program. It's just that extra atom shuts some of those things off. The whole training process is trying to figure out which ones are turned on and which ones are turned off. So that's kind of the basic intuition here. And this was actually introduced in the 2015 paper, but it wasn't solved with the neural architecture. I think they used, like a integer programming sort of thing. So let's make this concrete. Let's give an example. So we have a target that is Q, predicate Q. We have the extensional predicate P, and we have constants A, B, C, and D. All right? And so this is pretty much it. The slash is the number after the slash is the number of arguments for the predicate. All right. So let's say we have the following ground facts. You know, PAB, PBC, PCD. Okay, so we're going to just work through this one example. And we have the following positive examples, and then the negative examples. All this is saying, and using this non-ground notation, is it's just everything that's not in the positive. Okay? So we're going to assume two templates, and here is template one. So for the templates, they put different requirements on the templates in the paper. This one of them is the number of existentially quantified variables in the body. This will have none. An existentially quantified variable is just saying, hey, you know, let's say if Q of X is in my head of the rule, I can have an atom like P of XY, which will mean either, you know, there exists a Y, or in this case, if you extend it more, you could even say for all Y, but they look at the existential case. And no intentional predicates in the body, okay? So this template does not support rules that will be used in after the first step of inference. It can't be because there's no intentional stuff in the body. So in the notation from the paper, this is what it looks like. They have tau, and they say V is 0, and in for intentional predicate is also 0, and you know, Q is the target predicate. That superscript is just an index, meaning that this is the first template. In this paper, they limit it to only 2 templates, okay? Only 2 templates. And they do that because the number of templates appears in an exponent in the complexity result that I'll show you later. So it gets really nasty really quick. And we'll get into complexity a little later. Let's continue with the example. All right, so I'll show there's 8 clauses that can be generated with this template, and here they are. Now you got to generate all of them, but when you do, you can prune away some of the ones that are redundant. So that's what happens here. These go away. Or you can prune elements of the body that are redundant, but you also actually get redundant rules as you enumerate them. All right, so let's look at another example template, number 2 for this. And here, we'll change this up a little bit. 1 existentially quantified variable in the body and 1 intentional predicate in the body. So here's how that looks. And there's 58, and we'll show the 16. And by the way, in case you didn't see the subscript, this is all in Appendix B of paper. But you know, here's just a listing of them. And again, well, some of them could be pruned away. I think they were redundant ones weren't shown. All right, so let's associate these with some Boolean flags. So here's a set of Boolean flags. So that I index is for your template number. The J index is for the clause within that template. And the P is your intentional predicate. In this case, we just got the 1. So this statement here, all this is saying Fijp is true if and only if the clause is in the rules in your solution. And we already talked about the well, actually, in addition to the number of templates, the authors are only picking 2 clauses. And again, this is another exponent in the complexity result. Because they're searching a combinatorial space of combinations of rules. And there were some technical reasons as to why they went this way, as opposed to picking a subset like that. So here's your generated clauses with this guy tacked on. Other thing to note, the authors only allow 2 atoms in the body of each rule. Only 1 or 2 atoms in the body of each rule. Again, this is due to complexity. And here it is for the second template. No big surprise there. You just got those F's conjunction on the end. All right, so picking a set of Boolean variables. In this example, we're not going to say how it's done. That'll come a little later in the talk. But really, all this mathematics is saying is, hey, we're looking for a set B union F such that, for everything, for all the F's that are picked, the clauses union would then entail the target atom. And for everything that's outside of the positive set, they're not entailed. So of course, the set of rules, again, is just clauses such that the set F, this is just a set of these Boolean flags that are positive. And identifying the solution, in this case, if you make these 2 flags true, that actually gives you a solution. And so here are the associated clauses. And here's what those rules actually are. And this is a solution to this example. All right? So it's always funny in mathematics how I can give a super technical talk of just how it's set up, what the solution is, and I haven't told you anything about how it really works. That's always fun, right? Yeah.
I have a question. So I thought the first rule was proven in the previous process.
No, because it was only true if there was a duplicate.
But PXY and PXY on those.
Oh, yeah. So actually, you're right. You don't need the second PXY because it's conjuncted with itself. Okay, so, but it's not pruned, it's just a redundant element. Okay, so now let's talk about how we actually solve this. And this is kind of interesting. So the neural architecture, so the learning problem is they say, hey, we want to compute this conditional probability. I'll build this a little bit. So this lambda, this is the truth value for ground atom alpha. Alpha is one of your target atoms. So I'm looking at the probability of this value conditioned on that value being for alpha, the weights, the program template, the language, and the base set of facts. Okay. So no big surprise there. And there's what those all mean. And such that the following loss function is minimized. And this is a cross entropy loss over the pairs of atom and value of that atom in the ground truth. So notice we consider this value to be either 0 or 1 in the ground truth because we know the right answer, but in actuality it's going to be fuzzy, which is why we have the probability. So they like to say, hey, this is a one big conditional probability produced by this neural net, and we're solving for it, based using gradient descent. Okay, so they have these high-level constructs, and they say, hey, there's these series of these functions, and this looks really tough to follow, but it's actually not that give us that probability. And what's going on with two of the functions are really just translating symbols to vectors, and that's it. You know, so this is just saying, it's just giving you the value for that ground atom in vector X. This is taking a set of facts and it's giving you a vector where for everything in the set of facts, the associated position is 1, and if it's not in the set of facts, it's 0. It's like pretty simple. And we also have this thing that generates the templates. Again, this is just iter tools in Python or something like that. It's just enumerating out all the clauses for a given template. So when you look at all of this, really it comes down to F infer is the main thing that does the work. F infer is the actual neural network. And so you can kind of see in this flow here, what's going on is they have the axioms, which is the base knowledge set B, is just converting that into a vector, and then it has language and the templates, generates all the clauses. There's the clauses, the weights, initialized at whatever, starting point you have. Infer, this is, running gradient descent on the neural infrastructure. Here's your conclusion. Now you compare it with your target value. Cross entropy loss is what I showed you before. And that's kind of the flow of everything. So not too hard. I mean, in terms of big picture, it's really, really quite standard deep learning stuff we're looking at. So let's look at how this infer thing takes place. So we have this G, J, K, P. So JK is a pair, P is a predicate. And what this is doing is for these two Fs, it's taking the maximum of the two. And you can think of these two Fs. So you're taking that A vector. So the A, you could think of that as a vector representation of a set of ground atoms. Okay? What these two Fs are doing is for two of those clauses, one from the first template, another from the second template, because we're going to pick one per template. What one step of the inference process will conclude. Okay? So you can think of this as G, J, K of P. This is like applying the fixed point operator for rules J and K together on A, and it gives you vector representation X. All right? Now note vector representation X is only going to have non-zero values for things concluded by those rules. It's going to have 0 for everything else. That's okay, because that's all this little piece does. A is what they use. This is where all the weights, well, not weights rather, but this is where all the values for each of the atoms is stored. The subscript is based on the number of inference steps. So in the very first inference step, we start with all of the ground atoms in B get a 1, everything else gets a 0. No rules have been applied. All right, so this is kind of where it started, and this is what happens when, for two rules, the output that's applied. Okay, so notice that JK pair. So with that in mind, for a given JK pair at inference step T, C PJKT is just the application of G on A at time or at inference step T. Okay? And the reason we have all these subscripts is, remember, I said at the beginning, we have a limited number of inference steps. So the whole neural infrastructure is replicated T times, which is why you have that. So okay, how do we then update this across all JK pairs? So what we do is we have the result of the inference step, which is just taking a max. So notice, up until this point, I have not introduced any parameters. Okay? And we are picking a pair of those templates, or rules rather. One from one template, one from the second. Here we're looking at summing over all pairs, and we have that C vector from there. And now here is where we assign the weights. Okay? So B of T, BTP, is giving you the resultant inference of all the rules. And the intuition here is you could think at every inference step, I'm applying all the rules, but I'm applying them probabilistically. I'm applying all pairs of rules probabilistically. This is the probability at which I apply this one rule. I add them together, and the expected value is what updates in that B. Okay? So remember from before when we had that G thing, or this G thing here, the result of the G thing after input A is only going to change the atoms and the rule heads from these two rules, J and K. So for all these C's that I'm summing up here, except for conclusions of those rule heads, everything else will be 0. Okay? So I still have to do one more step. I have to add back in everything else. So that's where they come up with this F amalgamate. And notice this is the last step of it, or last piece of an inference step, because now I'm iterating my inference step by 1. So I'm amalgamating A of T with the sum over for, this is if I have more than one target predicate now, over all the B's, which was the result from the last slide for each target predicate. If there's only one, it's just the B from the last slide. Okay. So amalgamate, originally they wanted to do max, and they actually had an idea that, hey, if we use max, we can have arbitrary number of rules taken at each step. It turned out that in practice that didn't work. They had an issue with rules overwriting each other. And so they went with a probabilistic sum, which is why, if you remember from a little bit ago, we're looking at pairs of rules and we're taking the max from the pair. So in this way, we still get multiple rules, but they couldn't figure out a way to get around having pairs. There's been, I think, like 3-4 direct follow-on papers to this. None of them, could get around this problem. Yeah.
So, can you repeat again, like why they use the max in the first case? Why is it necessary to use that for the pairs?
So it's not apparent from this mathematics, but what you could do here is you could have for each, instead of having one variable for each pair of rules, you could just have one variable for each rule. So instead of having, I'll just say n, but that symbol is used for something else later. But instead of having n squared, you would have n rules, and then you could take max. You would have a bunch of things here, and then you could take the max over all of them, maximum value for that position. But they said when they did their implementation, that wouldn't give good results.
So if it's like an inference step, like that there are two clauses and then they give some inferences and we're taking a max, it's like more like a union over the words each of the clauses gives.
You can think of it as a rule that is a disjunction over the body of both rules. That's one way to figure it. Max is commonly used in fuzzy logic for disjunction.
So it could just as well be two separate rules.
So they are two separate rules, but what we're doing is picking a pair of rules. And so that's why they're doing it by pairs. So they have, if you remember the way they create that vector is by JK pairs. Other questions on this? Yeah.
Can you explain a little bit on summing up the B?
Oh, this
Why
is if you have more than one target predicate. So if you only have one, then you use two. And the reason why is because you're going to have a different set of rules for each target predicate, and all other positions in that vector will be 0. That's all. So you just add them together and all right, so one more thing is, so we had that function f that I just said, hey, the rule gives the result that goes into the vector, but I never said how it was done. The fuzzy logic behaves the same way as in logical tensor networks, and the authors explore, since the bodies of all rules are conjunctions, they just explored a couple different things. They found that the product T-norm worked the best, which is interesting because that's also what worked the best with logical tensor networks. They said that basically it had, the gradients flowed more evenly when you use product as opposed to using the other things. And that makes some intuitive sense. So let's talk about the complexity of differentiable ILP. And we'll talk about this in terms of the number of weights that are used, because that directly relates to space and time. So they talk in the paper about primary and secondary collection vectors. And so you are summing over the number of clauses for each template, for each target predicates, and one set of vectors you're multiplying by 2 times the number of ground atoms times the number of inference steps, and here is 3 times the number of ground atoms times the number of constants. In general, based on kind of how they approach the problem, one would expect the number of constants to usually be larger than T, but I think part of the reason why they put both there, because from a complexity standpoint, just, you would take the higher one. It could be doing it, in a theoretical correct manner with T. T is going to be equal to the number of intentional predicates times the number of constants in the worst case. So that would actually be bigger. And that's the classical case, even worse with us. So I did a little bit of looking because I wanted to see, okay, the number of templates is the source of complexity. The experimental results seem to show some scalability issues, and all the follow-on papers complained about complexity, but didn't show anything. So I thought, well, let's just kind of pencil it out here, and let's look at this, number of clauses that we have to generate. So that can be bounded by the following. So looking at the number of clauses per template, we can look at the number of predicates involved. So, which we're picking from the number of extensional predicates, and we got this int I, which is the number of intentional predicates that were permitted, because the template limits that number. But just to put it there, let's say that. And you've got a bunch of spaces to fill. So this is the arity, and this quantity here can also be expressed as a factorial. What kind of messes it up a little bit is you got this extra V, which is the number of existentially quantified variables you have. So whether it's factorial or this thing that's tighter bound is really going to depend on the values of these numbers. And then you got another exponent here for the maximum body size. So that's like a lot of stuff. Now, writing it this way with the product, Each template, these numbers are going to look a little bit different because you could have some templates, like you saw in the example, you have the one that had only 8 clauses and the other had like, 56, which was much worse. But for purposes of complexity analysis, let's just assume everything's kind of the same. Well, now that guy goes into an exponent. And so if you kind of use the assumptions from the paper, you get a big constant times the intentional predicates times p to the 4th, which is kind of big. But let's not forget, that's got to get plugged into the rest of this stuff. And so you end up essentially with, this giant constant, number of constants to the 3rd, number of intentional predicates, which that might be small, but you're quintic in the number of predicates. And then, so this is also what's been mentioned in several other papers talking about. They'll either say it's quintic or they'll say it's factorial in the argument size, but all amounts to about the same thing depending on the set of assumptions. So with that in mind, let's take a look at the experimental evaluation. So, we saw some exciting stuff, a little bit deflating to see the complexity results, but hey, they're DeepMind, they got the hardware for it, right? So training data, this was what I was talking about at the beginning. So training data consists of multiple triples, so multiple dILP instances for a given problem. And each step, one of the triples is sampled, and from the triple, they take a batch out of the positive and negative examples for that sample. And that's what they're using in a given batch. And they're saying in most cases, they're getting this done in 6,000 steps. They said cross entropy loss, as I showed you earlier, is what they used. They did try others. They didn't say what, I'm guessing mean squared error. They said the others worked pretty good too. That wasn't a huge deal. They used RMS prop with a learning rate of 0.5. They said Adam was good. They said it wasn't too sensitive to the learning weight, which actually I think is kind of good news there. And then clause weights were initiated from normal distribution over the 0, 1 error. So these all seem pretty reasonable. I thought the training setup was kind of interesting. Now, I really like that they included this in the paper, which is why I put it verbatim. But they made a point that when they would learn the model, that they would suffer from local optimas a lot. And the good news is, though, is because of what they call the inductive bias of the model, which is the ability to generalize, all they have to do is out of like 100 runs, they just pick the one that has the lowest loss. And that kind of makes a lot of sense to me because remember, they're dealing with learning non-ground rules, which are going to be more general. They also are doing this thing with the training data where they're picking the constants. So different mini batches are using different constants and they're kind of giving a little bit different view to push it toward certain predicates that tend to generalize more. And so because of that, they said, hey, when we pick the best one, it shows it works, ends up working very well. They also suggest that in future work, there could be things by inspecting the weights during training where you could just stop training after a couple of batches where it becomes obvious that, hey, it's heading towards that low optimal. But they didn't actually try that. They just didn't think this could be done. So one thing I want to show is difference between the various fuzzy t-norms that are used. And here we're looking at the percentage of runs with a very small mean squared error. And here in these problems, these are all like kind of very toy problems, like even odd is classifying digits as being even and odd. Less than is pretty obvious what that means. And then they have these kind of relationship things based on family tree and really tiny graphs looking at kind of graph problems like coloring and stuff. But bottom line here is what they list as differentiable ILP. This is using the product T norm, and it's the best in almost every case. To demonstrate the robustness to noise is they then looked at analysis of mean squared error based on partial data. How did performance degrade as they reduce the size of the training set, as we see here? And actually, it still does fairly well, even when you get to around half the data before it degrades completely in many of these problems. So they're maintaining much of the performance. And this was one of the main points of the paper. The paper was very focused on, hey, this is an approach for noisy data. They didn't make the case that, hey, we're doing, neurosymbolic reasoning for the sake of it. This is actually, we're solving a real problem here, dealing with noisy data that not really addressed in the ILP literature at the time. So they did some tests. Everyone likes to show, hey, if we tack a CNN onto our method, then we can do something cool with it. But this one is a pre-trained CNN, so not really end-to-end training. Although the interesting thing about this is a way to induce extra noise into it. So they look at, again, a proportion of successful runs based on pairs held out from training, and also look at mean squared error, how that goes. So not too bad. I mean, looking at, you don't really start taking off with the error until you're hitting, 60, 70%, and with the baseline, it's already exceeding quite a bit early on. Well, I'll open up to any questions. Yeah.
So that CNN baseline, did they use like EGG or did they use like an actual like known CNN benchmark, or did they kind of just use like a tiny CNN? They go into that?
So I don't think, I don't remember. I'd have to check the paper.
Okay, yeah.
It was for this one.
Yeah, because it'd be interesting if they use like a not so powerful model, it might not be as impressive, but yeah.
And the test accuracy 98%, whatever they used.
Yeah, they used the same thing that was proposed in 1998's paper from Lekon and Bengio. That's what they wrote. So they used that and then what Lucas mentioned. That's what you mentioned.
But I think in this case, to get an embedding to recognize the handwritten digits is not that difficult. You can have like a very simple CNN network to finish it very decently. So I don't think that's a crucial differentiator here. Like a very powerful CNN architecture and a very simple one in this case won't change much because the handwritten digit task is not that difficult. My personal.
No, also they don't go into the embeddings and all. It's just what they do is they have this notion of like image X, and then it just gives them some value between 0 and 1. So like 0.8 would be 80% probability that the image is that particular agent, and after that it's all about using that ground data. So it doesn't go into any detail about it. And it doesn't make sense.
Other questions? Yeah.
Yeah, so I had a question regarding complexity and also their results. So to me, like one of the big red flags was that, yeah, as you pointed out too, which is like all the tasks are very toy tasks. And so like despite this amazing performance, most of them like they sort of like put it under the rug, like the actual tasks are like the actual, the algorithm being general enough to handle more realistic tasks. I guess in terms of complexity or in terms of other things, in your opinion, what is the bottleneck
Well, the bottleneck is clearly this clauses generated by the templates because it blows up really quick and there's multiple drivers to that. You know, they did this in a very limited case. I will say after reading the paper a couple times, I don't think they were trying to hide anything because they were pretty upfront about being, you know, a memory hog and having, you know, big time complexity as a result of that as well. And they even have a section in the appendix where they said, why not a smaller model? And they talk about some of their empirical experiences that led them to down the path they did. I personally, I view this as, you know, a really foundational thing and just being able to show that it can be done. I don't think that clause generation by templates is probably going to be something that is used in the long term, but I think it was a nice way to, you know, see research this problem. Yeah.
So I saw that in the problems, and the examples they gave, they were saying that okay, let's say pred 1 is an input like intention predicate, and then it's learning how to where to put pred 1 or what to put the weights and stuff like that. And then in some problems they were giving pred 1 and pred 2, and it's quite obvious that which problems would need pred 1 or which problems would need pred 2, like two predicates. But that's obvious to ask, like why, like to me, like without doing any experiment, it feels like if you could give multiple predicates to learn to a problem which needs only one, then there's a chance that it might mess up, or there's a chance that it will learn the same thing. But giving the specific exactly the number of predicates seems like kind of giving some kind of an idea of exactly what it is to learn.
I think that's a fair criticism because the template is presuming some structure. And you know, it's kind of this funny argument that you say that, well, you know, we need to, you know, whether it's like learning a structure of a neural net or learning a logic program, they're both structural. Then when you do that, you find in a lot of the work, there's still some assumptions made about what kind of structure you're going to learn. And you know, I would tend to agree that, you know, these are, you know, somewhat strong assumptions about the structure. And I think that's a fair criticism of the work.
And the other thing is, noise is handling noise. So I think that in general the experiments are fine, but regarding the way they did it, so they mentioned that they sample a proportion of from a positive set and from a negative set, and then they flip it basically. They take the negative example and put it in the positive sample, and then the other way around. And like they show that once it goes above 0.5, the error increases significantly, but the entropy of the system reduces, and that makes sense because now my question is, initial part I understand completely because like increasing the noise, but eventually if you keep on taking the same number, same proportion and flip it, essentially aren't you asking the system to learn the other route, the opposite of what you want to learn? But most of the time noises don't come like that. Noise would be like, you know, like there will be like in the input, the false positives and the false negatives, they would not be proportional. And in this case, they keep increasing. Eventually, we're learning the opposite.
I mean, I think that on the surface of it, that seems fair. I think the analysis of that would be dependent on the balance of the positive and negative samples on how true that is, because it wouldn't necessarily be the case that it's imbalanced, especially in mixed region. You know, I think if you do consider everything you say and they are balanced, I think in many ways that is a good argument for why those particular group of results are strong, because degrades very gracefully up until 50%, and then by what you say, you would expect that after 50%, it's like all bets are off because it's essentially flipped. But yeah, I mean, so I'd have to look at some details to like say all that's for sure. I'll probably cut this question out of YouTube. Yeah.
I got lost in the middle. Like, can you give an example of where you said that pick J from the template one and K from the like JK pairs?
In the So J is an index over all clauses from template 1. K is an index over all clauses from template 2. And so for a given clause, this F function takes that input A vector and gives you a new vector that has non-zero values in anything that was in the head of the rule. And then does the same thing for the second. So this is for one pair, picking one from the other templates. And then later on, you see they're summing over all pairs, but assigning a probability to it using the weights. Get a follow?
So F is like a mapping function.
F is essentially like, it's like from LTN. It's like you have the, you could imagine neurons associated with stuff in A, and then going to a new neuron for what's in the head of the rule. And the activation function is the product T norm, and there's no parameters. Anything else? Yeah.
I got a question on the math test, on the result test. It's not in this picture. When doing the add even on, can you show that slide?
So did I have a slide for that, or is it in the paper?
No, it's in the slide. Yeah, it's
On this one?
yeah.
Yes.
How come is it so like performing so well compared to the other methods? I mean,
These are all differentiable ILP. This is just difference in the T norm. The column that says differentiable ILP is product T norm. This is differentiable ILP with Boodle, with Shevlets, and using max.
so
What is this? The max of those three. So, and yeah, the main reason why this is better is, they say that the gradients are distributed more evenly. And that kind of makes sense because this product is the partial derivative, one of the factors goes away. And the other thing that makes sense is this is essentially the same result that LTN's now, even though it's not an induction problem. They also found that the product T norm gave them better performance. Yeah.
I'm curious about first, can you remind me about what is the limit of how many applications of the fixed point operator they have? Like in other words, how many times do they basically make derivations?
I think in this paper, I think it was 3.
Right. And I'm kind of curious, so if they do things that are some of these tasks, right, are supposed to be recursive, and I'm curious how that relates to for instance, a graph calling task. In principle, you think you would need a lot more than 3 applications. And I guess they also make this comparison to differentiable programming. And so I'm curious how that limitation, I guess, compares to basically being able to do Turing complete problems like graph coloring. In other words, it seems like they basically you'd have to increase that significantly to actually be able to do some of these problems.
So effectively, it prevents you from doing those harder problems. So that's clear. that said with these small problems is they've engineered it where I think that, it doesn't need the extra inference depth. The other thing to consider is one thing about this approach that I didn't like is in general, what they're doing is they're essentially using the forward pass to compute their error in these tasks. And they said, hey, and then when you actually need to see the rules, just grab all the rules where the associated probability is like, 10% or something, right? And, because of that step where they're doing this kind of expected value over all pairs of rules, this is where it departs from actual logic. And this is why you can't just take that logic program and apply it and get the same results as the forward pass. It's because of this. Because you still technically need all the rules to get the same thing. It's the same with a small probability, I'm going to apply this obscure template.
It's kind of running like multiple rules in parallel, just waiting.
Well, all the rules are still there. Remember when I said at the beginning, once you generate the rules from a clause and you tack on those Boolean variables, all those things are in the logic program. In the classical case, the ones that have a contradiction in the body of the rules, they just go away. In this case, everything's still there. They haven't gone anywhere. You just have some guys with a really small probability. And so they're actually still there in a very subtle way. But you also have to think, okay, well, maybe those probabilities are small, so they don't matter. But we also have a combinatorial number of things. So maybe they add up, I don't know. My point is if you didn't have that, and you could just take the rules directly out of that, then I would say, hey, even if you limited the number of inference steps in training, it might still work on problems that require multiple inference steps. And the reason I say that is, if your training data, if everything in your training data has that limited number of inference steps, it's going to learn what was best based on the training data, and maybe it'll still generalize to something that requires more. We still got time if there's more questions. Questions from online?
Nope, nothing here.
All right, well, thank you very much. And, like I said, if you want another IPR, please sign up. Yeah.